Assalamu alaikum. In this video, we shall talk about carrier concentration in intrinsic semiconductor, and we will derive an expression for that. We know that at 0 Kelvin temperature in semiconductor, the valence band is full. That is, all the states in the valence band is occupied with the electrons, and the conduction band is empty. And there is an energy gap between these two bands. For silicon, this is about 1 electron volt. As the temperature increases, these electrons start to move freely within the boundary of the system. So electrons excite from valence band to conduction band. The excitation of electron could be because of heat, and also it could be because of light. When the electron excites from valence band to the conduction band, it leaves a void space which we call hole. At room temperature, a significant number of carriers excites to the conduction band, and then when a sufficient amount of voltage is applied across the system, these electrons contribute to the current. In this video, we shall derive an expression to estimate the number of electrons, the number of carriers available in the conduction band. To do so, first we need to know how many states or the density of states in the conduction band. We talked about that in a previous video. Then we said the density of state is the number of states per unit volume per unit energy range. And the expression that we derived in that video is GE equals this. Here m star is the effective mass. This is not same as the mass of free electron, because when the electron moves in the band, because of the curvature of the band, it looks like that it is a particle of a different mass, which we call m star, and named it as a effective mass. So in some region, the effective mass could be same as the free electron mass, but in other region, it may be different. And we know that the mass of a free electron is always a positive quantity, but the effective mass could be positive, and also it could be negative. So density of states gives us the idea about the states, how many states are there in a particular energy range. But we also need to know what is the probability of these states being occupied. For that, we will use Fermi-Dirac distribution functions. We know that electrons are fermions, so this distribution function gives the probability of an state being occupied by an electron at certain temperature T. So if we plot the distribution function, Fermi-Dirac distribution function, at 0 Kelvin, at T equals 0, the function is like this black line. This is a step function. So all the states below 0, where we have the x-axis is E minus EF, below this value is occupied, and above this is unoccupied. But as the temperature increases, the carriers from these occupied states move to the unoccupied states. That is, these states become occupied, and there becomes unoccupied. This is at this red line is at 150 Kelvin. At 300 Kelvin, you can see the line bends even more. At 600 Kelvin, it is even more. So this region, which we call tail region of the Fermi-Dirac distribution function, gives us the number of carriers in the conduction band at a certain temperature. Now, since we know that kBT is the energy related to the temperature T, And for the 300 Kelvin, we can calculate it. This is approximately 26 milli-electron volt, which is much smaller than this energy E minus EF of the electron, electronic energy. So for this region, to make the life simple, we can ignore the 1 in the denominator. So the distribution function, Fermi-Dirac distribution function, become like this with that. And this is actually the well-known Maxwell-Boltzmann distribution, or the classical distribution function. So for this approximation, instead of Fermi-Dirac distribution, we can use this one. Now we know that at room temperature, electrons excite from valence band to conduction band, leaving holes in the conduction band. Electrons start to occupy the states in the, leaving holes in the valence band. Electrons start to occupy states in the conduction band. So we assume that the bottom of the conduction band have the energy EC1, and the top of the conduction band has energy EC2. Same as in the valence band, the bottom has EC2 and the top has, bottom has EV2 and the top has EV1. But there is a energy gap between these two bands. So this is the energy gap. We call it EG. And the electrons are not allowed to sit in this gap. They can sit below EV1 or above EC1. Now we want to know this density of states for the electrons in the conduction band. So from the previous expression, we write it like this. Here, in writing this, we assume that the energy at this level is equal to 0. So we just shifted the origin of the energy and assume this to be 0. So the EC1 is equals to EG. Now, in this region, no electron can stay. That is, there is no states that electron can occupy. Above EC1, there are states. So when we assume this to be 0, the density of states in this region is 0, and it starts to increase as the energy increases from EC1. So we write it, the energy here is E minus EG. Now we have the distribution probability distribution function. We have the density of state. If we integrate the product from the energy range EC1 to EC2, it will give us the density or the concentration of electrons in the conduction band. But above the conduction band, the spaces are empty. There may be other bands, but let's assume the space is empty. So since we are only integrating within the conduction band, we can assume that EC2 to be infinity. That will make the life simple. And we have shown that here EC1 is equal to EG. So we have this expression with the values of f of E and g of E. G of E is equal to this. Now we like to make this exponential like this one, E minus EG. So we multiply with the exponential function E to the power EG divided by cavity. So this one become like this. And since we need to cancel the EG term again, we add it here. So they together cancel out to give us this equation. So this is same, but just rearranging. Now what we need to do, we need to evaluate this integral. To do so, let us change the variable. Let us write E minus Eg equals kVt. So we have dE equals kVt dx. And when the lower energy range of E is equals to Eg, then x equals 0. And when it's infinity, x is also infinity. So with this substitution, we have this equation. Sorry, we have this integral have this form. So now we need to evaluate this term, but this is a standard integral with the result of square root pi over 2. So when we substitute this value of this one here and this result in this expression actually, and we have n equals this. Here the this term also called the effective density of states of conduction band, and with this Nc, the concentration of electron in the conduction band is written like this. So this is the expression of the concentration of electrons in the conduction band. Now let's calculate the conduction of holes. Sorry, let's calculate the concentration of holes in the valence band. Now we know that the holes are these are the unoccupied states. So all the states are 1, that's 100%, and those are occupied are in this level, that is the unoccupieds are 1 minus F E. Here F is the Fermi-Dirac distribution function. That is this is Fermi-Dirac distribution function is the probability of an state being occupied by an electron. So the probability of an state to be empty will be 1 minus Fe. That is the probability of a state being occupied with a hole. So we put the this value here and we calculate the FH, and after some simplification we find this equation. Here also at this stage we neglected this one. Now we have the probability of an state being occupied with the hole. So we write the density of states for the hole like this. Remember, we assume that the states, this one, to be equal to 0. So when we use here minus E, actually this is positive because the energy is below here is negative, as the 0 energy level is this one. Now we have the density of states for holes and we have the probability. So we multiply them and integrate it from minus infinity to 0. So we assume that EB2 to be infinity, and we did it previously that EV1 is equals to be 0. So once we can do the calculation same with the as we did previously for electron, and we have this expression. So we have this the whole concentration. We can write it also like this, where NV is the effective density of states of the valence band. Now we have these two expressions. One gives the electron concentration in the conduction band, one gives the whole concentration in the valence band. But these expressions have another term, EF. So we want to get rid of this, the Fermi energy. To do this, we use the analogy that we know when an electron excites from valence band to the conduction band, it leaves a hole. So the number of electrons in the conduction band should be equal to the number of holes in the valence band. That is, these two concentrations should be same. So if we put these values here and we simplify, then we have this one. Here we have actually, they can both of the two cancel out. This one, this, and this cancel out, left it with MH and ME, and also this term and this term remains. So we have this one. Now here we have e to the power EF minus EG by cavity. Here we have e to the power minus EF by cavity. So we multiply it with, we divide these both sides with this term to have like this. Now we take ln, so we have this one, and after simplification we have if EF equals half of EG plus this term. Now this gives us the expression for the Fermi energy in terms of the energy gap and the temperature and the effective mass of electron and hole. So we want to use this one. Before we do so, let's examine this one. Since we know that the energy gap is about 1 electron volt, and we also know that the value of cavity at 300 Kelvin is only 26 milli electron volt. That is, this cavity at room temperature is much smaller than energy gap. So comparing to the energy gap, we can neglect this term. We can assume this to be 0. In that case, we have Fermi energy equals half of Eg. That is, for an intrinsic semiconductor, the Fermi level lies almost in the middle of the energy gap. Now, okay, we want to get rid of energy EF here. So we want to substitute the value of EF here, or we can do it here also. This should be the same because we know that N is equals to P. Let's do this. Let's substitute it here. So we want to rearrange it again so that we can just substitute here. To do so, we divide this with cavity, and then we have this one. Take an exponential, so we end up with this one. So we put the e to the power EF by cavity here, and we get finally N should be equals to like this. Of course, this is the same as P. You can do this in home. Substitute the value of e to the power EF by cavity. Substitute the value of EF here. Then you should get the same as this one. P equals should be same as this one. Now from this we can estimate the number of or the concentration of the carriers. So if we put Eg equals 1 electron volt, T equals to be 300 Kelvin, and assume that the effective masses of both the electron and hole is equal to the free electron mass, then it gives us the concentration of carriers or the electrons approximately equal to 15 billion in every centimeter cube. So this is the same for hole also. Since we know that N should be equal to P and that should be equal to this one, we sometimes call it intrinsic carrier concentration and write it as N subscript I. So Ni is like this one, and with the effective density of states, it is also can be written like this. So this is called the intrinsic carrier concentration. Remember, this is we derived for the intrinsic semiconductor where there is no doping. Now, if the doping is very small, this still holds, because you can see the number of carriers is 10 to the power 15 per centimeter cube. So if your doping is much less than this number, then this is actually high compared to the doping. So this expression still holds. Okay, that's all for today. Thank you.